All right, well, welcome everyone to the Access to Space panel. The previous panel that you saw this morning was end-state technology demonstration. That was, we've spent years developing a technology, and at this point we're ready to go and put it into an operational environment and test it, get that TRL-7. This panel is everything before that. This panel is the 4 to 6 technology demonstration, flight opportunities, other types of flight demonstrations type payloads. And so in this panel, we're going to talk about developing those payloads. You hear some panelists that are going to talk about how they develop their payloads under that environment. You're going to also learn about opportunities for flight and things that are coming online in the future. We're also going to talk about some lessons learned that each one of these panelists has experienced along the way. And of course, wherever your questions take us in between. So we'll handle some brief introductory remarks from all of the panelists in a similar fashion to how we handled this morning's session. And then we'll get into the Q&A portion of the panel. So we don't have the QR code up here, but if you have questions you can put them in on Slido. It's actually the first page of your pamphlet that you got. There's a QR code. Just scan that, put in your questions there, and then we'll have a conversation after all the panelists are complete based off of how those questions are voted. So I'll lead off with a brief introduction of myself. My name is Michael Johansen. I'm the flight demonstrations lead in STMD's game-changing development program. And my role is to oversee the development of our payloads and the processes in which we develop those payloads. And so one of the things that I've been really interested in lately is barriers to flight. What are the things that we can do as an agency and with industry and academia to reduce the barriers associated with getting your mid-TRL technologies some risk reduction activities through a flight demonstration? And if you are part of the LSIC fall meeting in fall of 2024, then you may be aware that we did a breakout session there where we had a survey and we handled some things like just asking the community some questions. And so coming out of that LSIC breakout session, we asked APL to do a deeper dive through interviews and other means to understand the things that are working, the things that need improvement, all that sort of stuff. And so if I could just plug for a second, on Thursday of this week, we're going to do another breakout session on that topic. So if you have an interest in having that conversation with us, I'd ask that you come by. And then finally, if you have done mid-TRL flight demonstration, you are probably familiar with the Flight Opportunities Program. And so Greg Peters is here in the audience. Raise your hand. Yep. So Greg is the program manager for Flight Opportunities, and he's here this week. And they also have a poster during the poster session this afternoon. I've learned that it's poster number 13. So if you have an interest in learning about Flight Opportunities platforms or anything else like that, I would suggest that you go have a conversation with Greg. He's a great guy. And with that, I'd like to start off our introductions with Evan from ICON.
Hey everyone, Evan Jensen from ICON Technology Inc., Vice President of Engineering and in charge of our Off-Planet Systems Lab.
Hi, I'm Jason Schuler. I'm the Principal Investigator for the ISRU Pilot Excavator Project, or IPEx, at Kennedy Space Center.
Hey y'all, I'm Jessica Piness. I am a Business Development Manager and Material Scientist, part-time at least, at Aegis Aerospace.
Hi everybody, I'm Rich Leshner. I'm from VAST. I do policy and government relations. It's nice to be here.
All right, thank you all. Evan, you want to kick us off with a brief introduction?
Sure, of our project?
Yes.
Yeah, our slides queued? Oh, I'm sorry, I have that. Okay, well, so I'm here to talk about Project Duneflow. It was a project that came to our inbox by way of our Moon to Mars Planetary Autonomous Construction Technology Impact Project by way of Flight Opportunities. And so I guess what I want to get across to this group as part of this short presentation, well, first, Icon is just a quick couple slides about us. We're a construction technologies company. We develop robotic systems for construction and software. This is our terrestrial print suite. This is the Vulcan system. It's a few years old now, having printed neighborhood at scale near Austin, Texas, where we're based. And then quick plug for Phoenix coming in 2026, which is our new additive construction system. So essentially, Icon is looking to change the way we build terrestrially, but we also focus some of our energy on off-planet construction for the moon and someday Mars as well. So that's what we're here to talk about. Just a quick intro on Icon. So we are working through STMD, a project run out of Marshall Space Flight Center called IMPACT, Moon to Mars Planetary Autonomous Construction Technology. Essentially, I'm going to talk about this tomorrow on another panel, so I'm not going to go into too much detail here, but it is relevant in that in order to do additive construction for the moon and Mars someday, essentially we need to manipulate regolith, lunar regolith, Martian regolith. It's challenging, as this audience pretty well knows. So as you see, those top two pictures are when we were doing a lot of scooping and tamping and filtering tests in collaboration with KSC, actually. And this is something that we actually use a lot of lunar simulant, and we work with it quite a bit, but we've also come to appreciate some of the downfalls and limitations of our current understanding of lunar simulant. So although the simulant that we're using in this case, I won't go into the details today, but it is about 99% chemically accurate. Geotechnically, it's not all that accurate. And so around this time frame, back in 2022, I believe, actually 2021, we got an email that was essentially saying, hey, there's a flight opportunity. What would you want to test? And so we were looking at the geotechnical or mechanical properties of lunar simulants, and we had this opportunity to fly on a lunar gravity suborbital flight. So how much fun would that be? And so what I wanted to get across to this group is that literally a quad chart that took less than 24 hours to turn around actually turned into myself and my team's first spaceflight hardware through flight opportunities in STMD. And so this proposal, I call this the initial design proposal. My two-dimensional quick turn of what this ideal was to study the regolith properties. And then this is actually 2 of the 4 panes of the quad chart, more or less. So the other one's missing our budget and schedule, which we don't need to worry about right now. So I call this the initial design proposal because engineers, when they got a hold of this, once we received positive indication that we might move forward with this project, they did what engineers do, and they slipped the scope and added complexity, which I love, but we ended up with a higher fidelity experiment because of it. So we took that initial concept and we added the concept of having these vacuum chambers as well, and we actually changed to simplify the design of the mechanical system to have this hourglass shape. So the whole reason we're doing this is to understand how these materials flow so that we can sort of close the loop and build better simulants. Icon was fortunate enough, shout out to the Texas Space Commission for helping us bolster our ability to produce simulants. So if you're in need, we're working on making higher and higher fidelity simulants out of our production facility in Austin. So get in touch. So this is the realized design, so full system CAD, and you notice that we learned a few things along the way because we were sort of concurrently engineering the system as we were getting requirements along the way. And you notice the lunar gravity vector is off axis from the way that the lockers are stacked, and that was a nuance that we sure didn't have an appreciation for at the initial design time, which drove some of the design considerations, things like number of channels, size of the apparatus that we were able to test in, the quantity of simulants, and things like that. So to move forward quickly, flight testing took shape. So we built this about a year or so into the project. We were into test. Out in 2023, thinking we were going to fly any day now. There were some schedule slips, as sometimes happens on the launch side, but we made it through our first spaceflight hardware through vibe testing, thermal testing, hazardous containment. So we needed dual containment due to the pressurization because this is going into a pressurized crew capsule. So one of the initial pitches that we had was could we actually use real Apollo regolith as not quite a control, but as a focus of our comparison? And so thanks to a partnership with Colorado School of Mines early on in the project, we were actually able to acquire temporary custody of these samples and fly real, no kidding, Apollo regolith samples back to space. And I was curious if anybody had ever put Apollo regolith back in space, so I asked AI. It said not publicly available. So hopefully the AI watches this and now knows that we have put Apollo regolith back in space. If anybody else has done that, please find me. I'm just very, very curious. I was not able to find that. So moon dirt back into space. So this is launch day. The top left picture isn't actually technically launch day. I cheated because I was allowed to show this photo, but it looked almost exactly like this, loading the apparatus before it gets loaded into the capsule. You can see at the top right, those little tiny lockers poking through the window of the crew capsule on the New Shepard lunar gravity. It's flight NS 29. And 9 minutes in, it's already parachuting its way down, having completed the experiment, and then on to T plus 10 minutes with a nice soft landing. So after T plus 10 minutes of flight, we got to wait T plus 3 more days to find out if our system actually triggered and activated and all of that, because it had no remote telemetry. But we did have success, and this is one of the results. Last 2 slides here. This is the delta between a lunar gravity and an Earth gravity, both in vacuum of our control sample. So this is glass beads, not simulant, not Apollo regolith. But some of the things we were able to correlate is the difference between gravity, and as well as the difference between having vacuum and having atmosphere in these different chambers. So last slide here, see if I can get it to play. So the interesting parts here, I'll kind of narrate. Bottom right is atmosphere versus vacuum of a simulant. So same simulant, different atmospheric conditions. Top right starts to get very interesting with the control. It flows just very beautifully. So we can compare that 1G to the 16G on the moon. And then the star of the show, left side, the 2 vertical in the column, are the Apollo regolith. And that top left one was just hanging on for dear life. With that 1G, the cohesion actually overcame its ability. So the gravity vector is pointing in the down direction on the screen currently. But you see right about now, the bottom left, maybe when he swings back around, and these are belt driven and phased together. So they're getting the same motion off the same motor per bank. And so right here, Apollo falls, but he bridges. So pretty interesting there to see that. So yeah, that's essentially it. So this data is under analysis and review by students at Colorado School of Mines, Dr. Chris Dreyer. So if you're interested in this data, please reach out to myself or Dr. Dreyer, and there is still time to collaborate on the academic paper, which is to be published this year.
All right, thank you, Evan. I'm also interested if lunar samples have ever been flown back in space. If anybody knows that, let's talk afterwards. Now they have. All right, Jason from KSC, you're up next.
Okay, so I'm going to talk about an experiment we did for the IPEx bucket drum flow. This is actually on the same flight the Evans experiment was on, the NS-29 with Blue Origin. So what is this for? This is part of the IPEx project. IPEx is a robotic excavator. This is some testing done this past fall at Kennedy Space Center, kind of going through a mock mission. But IPEx is unique in its design. It has these bucket drum tools that are these hollow cylinders with scoops that are staggered around the outside. The real innovation with IPEx is that you take those bucket drums and they dig at the same time but in opposing directions. And that reduces and really eliminates your need for traction to balance your force of excavation. So you can do excavation with a very low mass robot. IPEx itself is a little over 30 kilograms, and it is designed to bring back 10 metric tons, so 10,000 kilograms of regolith in only 10 days. So that is the state of IPEx right now. It's at Tier L5. We're under a GCD project. We started at Tier L4. We're taking it to 6 so that it will be flight ready. Looking for a flight to do a tech demo on the moon and show that we have the capability to excavate at this scale. One of the challenges we have with IPEx is the flow of the regolith inside the bucket drum, right? So, early on in the project, we asked ourselves, This works great, in the lab environment, even with, the best lunar simulants we can get our hands on. But when you go into a vacuum environment and then a lunar gravity environment, and you combine those effects and even electrostatic effects, what's going to happen to the flow of that regolith in that combined lunar environment? Will the regolith bridge? Will it jam? Will it affect the flow rate out of the bucket drum itself? And so, like Evan, we got this unique opportunity to do this extended suborbital lunar G flight and get 2 minutes of continuous lunar gravity in a small experiment where we could test some of these ideas out and see if we need to make changes to the bucket drum design so we could optimize this before we go build this version. When you're doing the excavation part of digging with these bucket drums, you're really kind of forcing that regolith into the scoops, right? So it goes in with this kind of forcing function of the drums rotating into the regolith. When you're unloading the regolith, it's really just the force of gravity that's pulling it out. It rotates around in this spiral baffle geometry. You can kind of see an expanded view of a bucket drum there. And so we really wanted to understand, do we need to optimize that baffle geometry? Is this the right spiral shape? Should it converge, diverge? Should we change the spacing on that? So that's what we're coming in thinking we need to optimize. And so you can kind of get a better picture of that here. On the left is our Tier L5 version of IPEx at Kennedy. And this is testing in the same test site you saw in the first video. So this is in Florida. Under a cover that we set up. We have a 70-foot by 130-foot long test bed that we set up to be kind of a ConOps test bed, right? And it's scaled appropriately for the area we'd want to do this tech demonstration mission. We have a mock lander. We have lighting that mimics the sun, low angle, really high intensity lighting. This is not the regolith high fidelity simulant test bed. We have another test bed for that in a different lab. So this is literally Florida dirt that we stripped all the grass out of, right, and got all the vegetation out of there. Happy to find that visually it represents close enough albedo that we can get imagery that would be similar to what we'd expect to see on the moon. When we go try to dig in that, you can imagine in Florida that soil is pretty moist, right? There's a lot of water in that soil, and it's very clumpy. The excavator doesn't do well with soil like that, right? It gets bridged up into the scoops and kind of clogs that area. So right there's an example of there's a type of soil, a type of regolith that you can put in the bucket drums and it won't flow, right? What if that's what it's like on the moon, right? We wanted to understand, do we need to make a change to the design? The picture on the right is us testing that's the exact same geometry bucket drum, just a 3D printed version early on, in a regolith simulant in one of our regolith test beds in a different lab. And it flows out no problem at all, no bridging. I wanted to understand, where we fall on that spectrum. So this is the payload that we built. There was actually 2 of them. We flew 2 what they call single lockers. And inside each locker, we have a custom vacuum chamber with a polycarbonate lid that you can see through and kind of see what's going on inside. Inside there are 3 bucket drum sections, right? So you saw earlier in the picture, a bucket drum's kind of built up with multiple sections into one kind of assembly. So we took these sections. These are scaled down, about 60% of the scale of what we actually plan to fly on IPEx. And we varied the geometry of the spiral baffle inside, and we varied the simulants that we put inside. So now we have a bucket drum with different regolith simulants flying under vacuum and then at lunar G. And here's let's see this place, kind of a little assembly just to kind of give you a little more detail of what that experiment looks like. On this top tray, we have cameras that are looking down through that lid of the vacuum chamber. The bucket drum sections are backlit by an LED panel behind them. The bucket drum sections have polycarbonate on the top and bottom. So you get this really nice silhouette of the flow of regolith inside the drum during the experiment itself. And then each bucket drum is actuated independently. We have an actuator that drives a spur gear connection, and so we can vary the speed and then a direction of the rotation of each of the drums. What this enabled us to do is kind of repeat experiments. So we were able to run an experiment at a certain speed, reverse the direction, reset the regolith, and then run it again, right? And so we got a lot of data from that. So I'm going to jump ahead Keep going for time's sake. So we had 6 different drums. You can see the different spiral geometries that we looked at and the different types of simulant. So we actually worked with one of the simulant providers at Exolith Lab to modify some of the simulants that we put into this. One of the challenges that we have as an excavator is that we get regolith that is right on the surface, right? It is the lunar surface. A lot of the regoliths that we get and have available from these providers, they're sieved down to particle sizes less than 1 millimeter. Well, that's not what you get from the lunar surface. You get little rocks and pebbles and everything too. So we needed to modify those simulants to actually mimic what we expect to see on the lunar surface. And because we wanted to test the cases, we did a kind of worst case fine and a worst case coarse simulant as well. And then we had a control of a glass beads. And then on the bottom left, you'll see that kind of highlighted in red there. That's what I call like the bubble volume. So similar to Evan, we can't dump this regolith out into our locker, right? You need to have it double contained. So we built this volume that would normally be outside of the bucket drum, that as the regolith flows into that space, the regolith has left the drum, and then we can reverse the direction it goes back in. And so that's kind of the area that we look at for flow measurements. So here you go. So here's some results. The bucket drum on the left, this is slowed down, by the way. We did 240 frames per second video. So this is the Earth version of the same exact bucket drum on the left, the Lunar G version on the right. The one on the left was run the morning of the flight in the payloads lab in Texas, and then Lunar G1 obviously during flight. And so you're obviously seeing differences in the regolith, right? You can kind of, I call it like a raggedness of the regolith, like the angle of repose, the breakover angle of this changes between Earth and Lunar G. But what I was really pleased to find is that we're still seeing flow, right? And one of the outcomes that we have from this is that no matter which bucket drum we looked at, what simulant we looked at, we always saw constant flow. We did not see any jamming or bridging. The volumetric flow rate of that was constant. We had 180 measured flow events, and so what I call like a flow event is regolith flowing kind of in and out of that bubble volume, right, if you will. So a lot of data from this. Some of our key findings is, that volumetric flow rate, it did not significantly decrease. And so that was big, right? We've been planning, trying to be conservative for a certain amount of time to dump regolith on the moon when we were doing a tech demo. Well, we found that we were being way too conservative in the amount of time that we planned for that. So we bought back 5.5 hours of mission time. In a 260-hour mission, 5.5 hours is a big deal. No regolith bridging or jamming. We had planned to do optimization on the spiral shape of this, but even on the scaled down bucket drum, we were able to see good flow on all the different designs. So we don't think that we actually need to optimize it any further for a tech demo mission. And then this one was extremely unexpected, and probably the biggest outcome is that the regolith density inside all of the bucket drums decreased under lunar gravity by 10 to 30%. Now that is a huge impact to our project, right? Because a bucket drum is volume limited. You can only hold so much regolith volume in it. Once you put more volume in, it starts spilling out the scoops on the backside. So if you decrease your density, that means you're bringing back less mass of regolith every time you fill up those drums. And over the course of our mission, if it was up to that 30% level, that means we're bringing back 3,000 kilograms less regolith than we expected. So it kind of makes sense, kind of in retrospect, looking back at and seeing that makes sense, that phenomenon. But it wasn't on our radar, and I don't know that it was on anybody else's radar either. So doing this flight experiment really reduced the risk and kind of increased the productivity for our future tech demonstration. And finally, we have a public-facing website. Please go ahead and scan the QR code. It does work while it's spinning. And we're releasing all this data. That is part of the IPEx project, is we want to infuse everything that we're doing to the community, and it is open and as much as we possibly can. So please go check it out. Thanks.
All right, so speaking of QR codes, make sure you get your questions in for the Q&A session. Up next, we have Jessica from Aegis Aerospace.
Yes, hello y'all. I am Jessica Piness. Like I said, I'm a business development manager at Aegis Aerospace, although my background is actually in materials engineering. And one of the things I really love about my job at Aegis is that I actually get to use and work on some of the platforms that I got my PhD data from. So it's a very cool full circle moment for those of you who are maybe just starting in your careers. So we are a small business, a women-owned small business located out of Houston, Texas. We're a couple blocks away from JSC, and we do have facilities at JSC and KSC. We do love visitors, by the way, so if you're ever in the area, let us know. Now, a lot of people may think Aegis is a new company. We, just to give you a little background, have been around since 1992. We were originally founded as Muniz Engineering. We've been through a few name changes, spin-offs, mergers, et cetera. We are now Aegis Aerospace as of 2021, but we are still the same company that started in 1992 with a contract with the DoD Space Test Program to do payload integration services on shuttle. So over our 33 years, we've really focused a lot on payload integration, flight ops, and in situ testing. So while these folks here have talked to you about very specific experiments, I'm going to take a step back and talk to you about our testing platforms and hopefully get across to you the message that the access to space, it's here now. We are ready, and we've honestly been doing this for close to a decade now, to test your samples in LEO and beyond. So one of our main philosophies we call STaaS, or Space Testing as a Service. And really what it is, like I said, a collection of these test platforms that we have in different locations that can test your materials or devices in situ. We started with the MISSI, or Multipurpose International Space Station Experiment. That was originally, some of y'all may be familiar with the very original MISSI suitcase material science experiments. In 2015, we won a contract with NASA, and it was actually a public-private partnership. I know Nikki was talking about those earlier, so we have a lot of experience in those too, where we have created a commercial version of MISSI that is on the outside of station that I'll talk about in a little bit more detail in a minute. We also, although it's not on this chart, we do, again, continue to do work for the DoD Space Test Platform, or Space Test Program, with their own platforms on ISS as well, although those are not commercially available. What's also not on this chart, because it's brand new, we got an award very recently from the Texas A&M University System to create their own version of MISSI on ISS. And an award from the Texas Space Commission, and I think Icon was mentioning their award as well, to further develop a platform for in-space manufacturing. So one of the themes that you'll see as we kind of progress through these platforms is, right now we have what we call space testing as a service, but honestly, internally, we're talking about, well, maybe that should be space manufacturing as a service, or space access as a service, or something like that. So we're actively thinking about how the industry and how what we do in space is growing and evolving. We also have a free-flying satellite called the M1 bus, as well as 2 lunar platforms, RAC-1, which was on the moon 2 months ago, thank you Firefly, and STEF-1, which will be on IM-3. So MISSI is kind of our bread and butter. The way it works is it is what we call flight facility installed on the outside of the ISS. We, on the ground, take your samples, whether they be small squares of materials, which of course are my favorite samples, or your active devices, let's say sensors, cameras, really small processors, really anything that can fit in about a large shoebox and takes about, I believe we get about 50 watts per carrier. And we package them all in a carrier, seal up the carrier, it goes up in a capsule, goes through the crew volume, out the GEM airlock, and is installed, our carriers with ISS robotics, and then the carriers actually open. So the carriers remain open for at least 6 months, exposing, again, your material, your device, whatever it is, to the LEO environment. And we have different stations or different areas, weight, RAM, et cetera, so you can get different environmental effects. And again, we can fly both passive material science samples, but we can also fly active samples that are powered, that require comms. I have Jeff, who is our operations guy, who's here, and he's actually going to give a great talk on rack and stuff tomorrow. But yeah, we have flown for all sorts of companies and government agencies testing various sensors and devices. And like I said, this is really our bread and butter. Now this is LEO, and I know we're at LSIC, and the L does not stand for LEO. But we have had technologies. I think there was a technology shown earlier today, one of the electrostatic dust repulsion, that if you notice, was originally flown on MISSY as a proof of concept and is now on the moon. So just because it's LEO doesn't mean it doesn't have a place in your roadmap, whether you're going to the moon or to Mars or to wherever. Again, we also have a free-flying satellite bus. I'm not going to talk as much about this because this is more of a DoD application. We've flown this as actually kind of twist of fate, ended up being the first Space Force satellite, even though it was commissioned by the Air Force. This is deployed off of an ESPA ring or ISS. And again, if you're looking to do anything from testing to manufacturing in low Earth orbit, geo, or we could even do cislunar with this, again, we're the folks to come to. But then, of course, the stuff that everyone here gets really excited about, the lunar platforms. So like I said, we have 2 of those. But again, there's still very much our way to enable folks to have access to the surface, to do testing, to do technology development, to raise TRL. So our first platform is the Regolith Adherence Characterization, or RAC-1 platform. That was basically, it was a material science platform, and what it did was it exposed certain materials selected either by NASA or by private industry to regolith. On the outside, is mounted right on the outside of Blue Ghost. If you've seen that kind of white rectangular box on the front of Blue Ghost, that was us. And we had a really, really great time, again, flying with Firefly, and then we were able to take pictures of these samples over, we took about 5 pictures over the full Blue Ghost 1 mission. And we were able to see how much regolith was deposited day by day. And again, Jeff is going to give a more in-depth presentation about this tomorrow, and we're going to be at the technology showcase again tomorrow with a small model of rack. And you'll get to see some very interesting stuff, such as we noticed regolith accumulated on our samples after landing, and then after a few days, the regolith went away. And we're not quite sure what happened there. And as a material scientist, I'm putting on my thinking cap. If y'all have ideas, let me know. But it's very interesting. And then we also have Steph, and I have the qual unit for Steph with me, actually. If any of you were in Baltimore Airport yesterday, I was the crazy person with the giant cardboard box. But this is going on IM-3. We named it Steph because our owner's name is Steph, so of course we have to memorialize her. But this is another testing platform, and I should say this was actually a tipping point award. So thanks to STMD and their Tipping Point program. And this is again, kind of a NASA and public-private partnership in a way, because we own and operate Steph. We used NASA funding to do what could be argued to be the first ever buying of lunar cargo services from IM. And then we went out and found folks who were willing to fly experiments on Steph. And again, Jeff will have more of this tomorrow. You'll be able to see more at our booth. But these experiments range from things like just radiation sensors, solar cell testbed, different computational experiments, and so on. So again, it's powered. We operate it during the lunar day, and so on. So overall, I think that is my last slide, but again, I really want to get that message across. I'm so glad that we were asked to be on this Access to Space panel, because I hear so many people talking about getting to space. And I really want to get the message across to y'all that we're already there. If you know, come talk to me, we can get you in LEO. We can get you to the moon. You know, let's go.
Excellent.
All right, thank you, Jessica. And now rounding out the presentations will be Rich from VAST.
Okay, nice to meet everybody, thanks. I'm gonna press the button and hope a video doesn't play just yet. Okay, good, we're gonna leave it there. An aspiring picture of space. All right, so VAST, we're a Long Beach, California company. We are an aspiring commercial space station company. The reason I say aspiring, the company has an ethos that we won't be a commercial space station company until we have actually launched a commercial space station, operated it safely, and sent crew there and returned them home safely. But we are actively building our very first space station. It's called Haven 1, and I'll talk about that a little bit more, and we'll see some stuff in the video. But we are one of a handful of companies hoping to, aspiring to, intending to be the replacement space station, or hoping to build the replacement station for the International Space Station, right? So the ISS is planned for retirement in 2030. The Commercial LEO Destinations Program, CLD, is the initiative to replace it with a commercial space station that NASA would work in partnership with industry to utilize, public-private partnership modeled on commercial orbital transportation services, COTS for access for cargo to the ISS, commercial crew, which followed later, and now CLDs for the actual destination. We got started, VAST got started relatively late in the game of CLDs. So CLD phase 1 was in 2021, I believe. Our company was not founded at the time and not able to compete. And so in order for us to be able to engage effectively and have a chance at winning, we developed a strategy backed by our founder and first CEO, Jed McCaleb, to actually go out and build a space station and get it up to space and operate it safely and send crew there and return them all before NASA was due to make its decision about who its long-term partners would be for the next phase of CLD. And that space station that we will be launching in about 12 months from now is called Haven 1. And what I want to show you now is a video of us going through the process of building Haven 1, manufacturing, and doing qualification testing on the primary structure qualification article for Haven 1. So this is a recent shot from a test stand we have in the Mojave Desert at the Air and Spaceport there of the qualification article. When we got started on the plan, we wanted initially to try to get as much supply chain support as possible from the industry, but it turned out the supply chain wasn't necessarily robust enough to build all of the things that we needed to go fast to build a space station. And so we are doing some of those things ourselves, like the control momentum gyros that you saw, like the valves, but we do have some partners like Impulse, I think, for our thrusters. We have DHV to provide solar panels. And we're not just starting with Haven 1 as a space station. In fact, we are building out something called a Haven demo satellite, which will demonstrate our comms architecture. It will flight demo our avionics package and our flight computers. And I think there's a picture coming up. So we are very much a vertically integrated company trying to bring in-house as much of the key manufacturing capabilities, test capabilities, design capabilities, and operational capabilities required to have as efficient an operation as possible for the next generation of commercial space stations. So all of that goes into this article you see here, or you saw there briefly, that is on the test stand now at Mojave. We also are doing our own MMOD, micrometeorite and orbital debris shielding. And that is the primary test article for the primary structure of Haven 1, sort of going through some welding. And now it's going through active testing at our test stand in Mojave. And the next step is actually manufacturing the flight article for the Space Haven 1 station that'll launch in 12 months. This is a few months old now, so this is the first weld that happened for the primary structure for the flight article, but it's much more further along. I just didn't have marketing's permission yet to show the most updated video, so I ask that you keep checking the VAST page on YouTube to see the latest video, because you'll see a little bit more progress. Okay, so we're building a space station. Pretty cool. There was a 30-second, or less than that, I guess 3-second little snippet where it said Haven 1 payloads. So let's talk a little bit about that. Haven 1 itself ultimately is going to be a 10-meter long by 4-meter diameter aluminum cylinder. The total pressurized volume in there is going to be about 80 cubic meters. The habitable volume is going to be about 45 cubic meters. And there will be something that we call Haven 1 Lab. Haven 1 Lab is the equivalent of an ISS Express rack. It is 10 mid-deck lockers. And mid-deck lockers are about 50 by 40 by 30 centimeters-ish. Somebody once said it's about the size of a microwave, and I said, not my microwave, because my microwave is tiny. So I hope it's bigger than that. But nonetheless, those are experiment racks. Each will get about 100 watts of power that are available for the kinds of experiments that we've talked about here. Now, initially, Haven 1 is going to be a microgravity lab environment. Of the 10 mid-deck lockers, we have 5 commercial partners signed so far. We have Redwire, Yuri, Interstellar Labs, Exobiosphere, and a company out of Japan called JAMS. And the bulk of the utilization that they plan for their part of Haven 1 Lab will be in the biological sciences, plant growth, cellular biology, things of that nature. But we know we are investigating actively with other potential partners for other kinds of sort of, we'll call them, or I'll call them sort of mechanical experimentation and demonstrations, technology demonstrations. So more news will come on that. In terms of operations, Haven 1 ideally will launch about 12 months from now. Right now we're still saying not earlier than May 2026. If all proves well, we'll launch crew on a Dragon about 2 to 3 months later. And then every 6 months thereafter, we will send another crew rotation until we've sent a total of 4 crew rotations over the course of about 2.5 to 3 years. But I think potentially of interest to this group is that after the 3rd crew rotation, when there's no crew on board in between the 3rd and 4th crew increment, we will be rotating Haven 1 so that in that Haven 1 lab space, we will be generating lunar gravity about 1.6 G for about a week. I think it's a week. And so we're very excited about the prospects of simulating lunar gravity for that amount of time and seeing how all of our existing and future Haven 1 lab partners will sort of utilize that opportunity, what they could learn from it, what tech demonstrations they could do, what they might learn in terms of cellular biology changes being affected by the exposure to different kind of gravity over that period of time. So it's an exciting opportunity. I think as a continuum here, right, we are in that same area that Jessica is in with respect to, services and opportunities for access. And we are, at present, Haven 1 is a pure commercial play, right? Haven 1 is built entirely and funded entirely on the funding contributed by our founder and additional funding that we plan to raise in the private market soon. I mentioned the commercial partners already, and we are not yet ready to announce who our crew will be. But in total, we are not yet a government-backed or government-funded operation. We certainly look forward to announcing some great partnerships soon, and that'll only add to the story of the opportunity for folks in the private sector and folks in government to be able to leverage access opportunities that come from new commercial investments and public-private partnerships with folks and companies like VAST in the future. So that's it. Thank you.
All right, thank you. So a question to kick us off. How do you balance the need for rapid iteration in technology development and demonstration with the rigor required for the space environment?
I'll take it. So the group that I work at Kennedy Space Center is called SwampWorks, and part of the Granular Mechanics Regolith Operations Lab. Part of our philosophy is rapid iterations, right, and failing fast forward, right? So we really believe that you're not going to, even for these kind of tech demo, these higher risks missions, get to a point where you're going to sit at a computer, design it from start to finish, go build the thing, and it's just going to work that first time, right? Like that's just never been our experience in any project we've ever done. So what we do is we build iterations quickly, and we learn from them, right? That first one you build, maybe you missed some things, but maybe you find something out that you never would have caught until you build that final version and test it, right? So for me, it's that, right? You start with rapid iterations, and then fold that in, and then in the end you get a better product.
Just to add to that, I think there's an opportunity here through flight opportunities to increase your posture for risk by bringing down what's at stake in terms of budget and schedule and such. So just by, for instance, on the lunar gravity flight, we had an atmosphere inside the crew capsule, so thermal was much less of a problem for us. So we didn't necessarily have to design something as if it were going to the moon, but we could learn as if it was going to the moon. So just really, I guess that would be making sure that the scope is applicable to your schedule and budget, and not trying to do too much at once, whereas we were able to learn quite a bit about software and avionics and shock and vibe testing, for instance, but we did not use flight computers because the bar just wasn't high enough to warrant that. So that's another way to do that.
If I may chime in with yet another way, I know one thing at Aegis, and I think a lot of you are very concerned about with the end of life of ISS, what happens to up-mass and down-mass subsidies, what happens to cases, things like that. And so one thing we're pushing for is more in situ characterization and more in situ iteration. So currently with Missy, let's say you fly your coding, it goes up, stays there for 6 months, comes back, you analyze it, you figure out what you want to do next, and then you repeat that process. We would love to move to a process where maybe you are doing some sort of microscopy or, I don't know, hardness testing or TGA or spectroscopy or something like that on your material in situ, and then maybe you could have a 3D printer or some sort of reactor or something producing a newer formulation, right there and then. So you don't have to spend the time and the cost to constantly fly back up and down. Now, there are obviously other issues with miniaturizing instruments. I saw that Flight Opportunities in their Space Technology Payload Challenge, they did call for miniaturizing instrumentation. I think it was everything from microscopy to, I believe, an NMR was listed. I was like, whoa, if you can figure out how to minimize an NMR to like that big, please, you're going to win a Nobel Prize or something. But overall, I really also think that the more we can do actually in situ, the better.
Thank you. All right, so going to Slido, again, go ahead and vote for your questions or put in additional questions if you have them. But the top rated question here is to Icon. What is the first construction experiment that you think is essential to take to the moon?
The first construction experiment to take to the moon, you should join the panel tomorrow, where we're actually going to talk specifically about that. But really what I like to focus on more is what processes are available and what is the lowest barrier to entry to prove those processes and close our lab testing. So we can test quite cheaply, relatively speaking, of course, here on Earth in labs and in TVAC chambers and all of those things. But specifically, the actual project is a lot less important than being able to anchor the modeling results and the lab testing results. So check out the panel tomorrow around this time.
Great, thank you. So I think this one is good because it addresses, I think, all of the panel members. So what interoperability challenges are you facing to make your capabilities more available to different partners and providers?
I can actually take that one if you like. So as you know, we have platforms on the ISS, and we are looking and actually talking to all the CLD partners, including VAST. I kind of include y'all in CLD, even though I know you don't officially have an award.
We'll take the label.
And that's actually an active struggle we're looking at is, okay, well, how will we get from ISS to a CLD? Or what would the new CLD's requirements be? Can they even host external payloads? And I think that could really be an opportunity for NASA or someone to come out and almost be the forcing function of, well, this is the interface you have to use, or these are the standards you have to abide by. Because right now what we're seeing is a lot of, well, I'll fly your payload, you tell me what you need, and we'll say, okay, well, what do we have to do to hook up to you? And we'll just kind of look at each other, and you know, there's some good conversations, but that is, I think, a really big challenge that I wouldn't say has been figured out yet.
Yeah, I would, on the similar, but maybe on the flip side, one of the benefits of the ISS operating for as long as it did is that mid-deck locker standard, right? So that at least when it comes to, now there's lots of stuff. There's power, there's temperature control, there's data connectivity. There's a lot that's still sort of to be determined, and every CLD provider is probably thinking about that in a different way. But at least maybe one of the things that's a little bit locked in is like the sense of geometry, right? If it's
Internally.
yeah, that's right, internally. Is it a one mid-deck locker? Is it two? Is it four? But you can speak in these, sort of like the CubeSat standard, you know? Is it a 1U, a 3U, a 6U? You can have that. Maybe that part of the conversation is retired a little earlier so you can get onto the other more difficult parts of the conversation.
What about from the payload developer side?
Well, I was going to take it a slightly different way, but you know, from excavation standpoint, right, with IPEx, you know, I think about our demo, our tech demo is really the tip of the iceberg, right? It is a whole paradigm shift for robotics for NASA, right? This is the first robotic construction worker for space instead of the robotic scientist, right? We drive more in 10 days than a Mars rover does in 10 years, right? The operational rates are just completely different, right? But again, it's scratching the surface, right? We want to get to a point where we're operating for years at those rates. And when you get to that point, you'll hit repair and maintenance needs where things just wear out, just like they do on mines here at Earth, right? You get to a point where you have to go just replace that part because you just can't engineer it to last any longer. And so that's where I start thinking about interoperability is when you have equipment on the surface operating at those rates, you're going to be swapping components for repair and maintenance needs. It would be a real shame if every piece of equipment had a different standard for those interfaces, right? And didn't be able to swap components with each other. So I see that as a big path for us for excavation and construction moving forward is kind of solving that challenge where we can leverage each other's work and have common interfaces.
Yeah, just a quick plug for the breakout session on day 3 for DARPA's Logic, where this is the top topic is interoperability challenges. So from a payload integration standpoint, I mean, we didn't focus on it too much. I think we could have done better as a larger group to communicate earlier about who had overlapping functions, essentially. But all the way down to, you know, we have a bespoke interface that was designed to Blue Origin's avionics, which you can find the specification in their payload user's guide, but I bet you don't find the same specification in the Intuitive Machines or Astrobotic or XYZ, you know, CLIPS catalog. So though those things are in work and people are thinking a lot about them, I think that it's a hot topic. We'll just say that. It's a hot topic, and you should join the Logic breakout session.
All right, thank you. So I think we have time for just one more question. We'll do rapid fire with the panelists. What is the biggest lesson learned that you have, through your development and demonstration that you can share with this audience?
You go first.
For me, without a doubt, it's the density finding that we saw, right? That is, like I said earlier, immediately impactful to our future mission, right? We could have gone through this entire flight hardware development, done the flight, and if we would have saw that same phenomenon on the surface of the moon, we wouldn't have hit our KPPs, right? Just from that one thing. If everything else would have gone completely perfect, that one finding would have made that difference. So doing that early for a relatively low-cost suborbital flight now enables us to reduce the risk for that future tech demonstration and get better data. So.
I'll swing back. I was trying to decide technical or more programmatic, but technical, we still have a lot left to learn about our data, so I'll save that one for when those findings are all in. However, I think what we could have done better as a payload developer would be to have pushed back early in the process to get communication across the payload array of payloads that were launched. I forget the number of payloads, but in the teens, certainly. And we didn't really know what each other were doing until almost integration day, actually. And so if you notice a lot of similarities between, we could have shared the coatings on the glass that we evaluated pretty extensively, and you could have benefited from that. And we both had camera systems. There were, almost every payload had a camera system. So now coming into this, if we fly again, or if flight opportunities, I would love the opportunity to workshop and find out which sort of Legos we have to put together experiments in similar form factors doing similar things. So I'd say that would be my number one lesson learned is collaborate early and often if your intellectual property allows it.
I think I'd add to that, one of the things I know I've learned is that this is just an incredibly complex ecosystem that we're in. If you think about it, it's not just, is there a space station there? Is it there messy? Is there rack? It's how do I get there? Who, if anyone, is subsidizing the flights? Who is operating it? Where do I get my power from? Where, there's all these different factors, and I think we don't fully appreciate that. Something as little as, just doing some outreach about your project, let's say to a local school, that can affect someone who then goes and calls their representative, which then means NASA gets, hopefully, more funding, which then means maybe you get another experiment. There's all these little ripple effects, it's all very interconnected.
Thank you.
Yeah, it's a tough one. I don't want to speak for the engineering teams since I'm not on the engineering team. VAST, I'm going to share a personal lesson learned that's repeated in my time at VAST. So VAST is the second startup I've been at since leaving government 11 years ago, and both of them are vertically integrated, so a lot of value on co-location and co-mingling of design, manufacturing, and test all in one location, and the sort of value that comes from not just the reduced cost because of the sort of no transaction cost economics if you're using a lot of suppliers, but just the proximity of the human capital to sort of learn in real time with each other. That's not the lesson learned, but I want to say in addition to that, I think the lesson learned that was sort of double tapped, if you will, for me in learning about experiences of our engineering team at VAST, I'm going to speak to very specifically. We have a ECLIS team, environmental control and life support systems team. We have a trace contaminants team that's been working very closely and actually posted some stuff on social media about lessons learned and really TRL advancement we've gotten from working with the ECLIS and trace contaminant experts at Marshall Space Flight Center. And so in the company I was at before, Planet Labs, there was a lot of expertise gleaned out of the NASA remote sensing folks when it came to like instrument calibration and sort of how to do good validation of your remote sensing instruments. And so I would say that a thing that I'm constantly reminded about is the quality, depth of expertise, professionalism, and desire to make the community better that it exists at NASA, and how that's a benefit to the country.
All right, thank you. So with that, this concludes the Access to Space panel, and if we could just give a round of applause for our panelists.